We usually think of history as, well, just a bunch of random events, right? A king gets crowned over here, some discoveries made in an isolated lab over there. But every once in a while, the universe just seems to perfectly align on a single, astonishingly productive date. And July 15th is absolutely one of those dates. In fact, you could argue it's one of the greatest dates in the entire history of math. So let's dive right into this explainer. Because on this one specific date, across completely different centuries and completely different countries, brilliant minds were quietly asking questions that fundamentally built the modern world we live in today.
Our journey today maps out across 4 distinct eras, all tethered to this one single day. We're going to traverse time from Abul Wafa in 998 to Mary Taylor in 1898, Henryk Zygalski in 1908, and finally Dudley Woodard in 1965. Across these radically different periods, these folks set out to solve some seemingly impossible problems. And by doing that, they laid down the invisible mathematical infrastructure for things we can't live without today, like GPS, global Wi-Fi, and the internet. Let's jump into the first mystery. Think about your morning routine for a second. Have you ever actually wondered how your phone's GPS or Google Maps always manages to find the absolute fastest route, even with hundreds of possible roads and detours? And beyond that, how is it physically possible that a tiny little rectangle in your pocket can talk to space to pinpoint your exact location, anywhere on Earth, in literally seconds? When you stop and really think about it, the sheer complexity of that routing is just staggering. To understand that modern miracle, we actually have to go way back, over a millennium to be exact, to July 15, 998. This brings us to a brilliantly minded astronomer and mathematician in Baghdad named Abul Wafa. Back then, trying to measure the cosmos was, frankly, a daunting task. Telescopes hadn't even been invented yet. So measuring the sky required an entirely new mathematical architecture. Abul Wafa created highly accurate tables and methods for measuring triangles, specifically so he could track the precise orbit of the moon and the stars. And the real kicker here, his precise math for measuring triangles in the sky is the exact same foundation we use for satellite navigation today. He mapped the stars, and now that exact same math maps your morning commute. Just look at this staggering stat. His tables were accurate to 8 decimal places. I mean, we're talking about the year 998 here. No digital calculators, no computers. Abul Wafa achieved a level of mathematical precision so profound that it became the literal foundation for modern trigonometry. That hyper-accurate math, which he originally designed just to understand celestial bodies, is exactly what allows your map app today to precisely calculate the distance between 3 orbiting satellites and your car. So, that was our first profound leap on July 15th. But now, we're going to jump almost 1,000 years forward to the year 1898. A completely different era, an industrializing world, and an even bigger idea. Let's fast forward back to the modern day for a second. Have you ever wondered how your phone catches an invisible song straight out of thin air? We totally take it for granted that we can just walk down the street, streaming a Spotify playlist, or loading up an HD video without a single physical cable attached to us. How does wireless internet actually get to us? Why do those signals navigate the atmosphere perfectly instead of just, scattering into the vast nothingness of the sky? Well, the answer points right back to July 15th, 1898. That happens to be the exact day a brilliant mathematician named Mary Taylor was born. She devoted her work to something called the magneto-ionic formula. Now, don't let that complex name intimidate you. Simply put, radio waves don't just travel in a straight line forever. If they did, they'd shoot straight out into space and be gone. Instead, they interact and bounce off the Earth's ionosphere. Taylor mathematically mapped out the deeply complex physics of how these invisible waves travel, bend, and bounce through the atmosphere. By proving exactly how they behave, she proved that global, reliable wireless communication was physically possible. And what made Taylor's work a real game changer was that she elucidated these complex formulas for experimental workers, basically the actual boots-on-the-ground engineers who were trying to build the very first wireless radios. She didn't just keep the math locked up in an ivory tower, she translated pure theory into practical engineering. She essentially gave them the exact rulebook for how invisible mathematical waves propagate. And because she did that, the streaming music and the text messages you request today arrive at your device perfectly intact. Okay, still on July 15th, but just 10 short years later, in 1908. We're moving away from the birth of global communication and into a very different time, a time of devastating global conflict and intense secrecy. Let's think about modern security for a moment. What actually stops a hacker from reading your private passwords? When you send a secure text or log into your bank, your data is scrambled using heavy cryptography, stuff like incredibly robust 256-bit encryption. But at its core, what keeps that scrambled data safe from prying eyes? How do we first figure out how to reliably lock and unlock digital information?
That question brings us to July 15, 1908, the birthday of a truly remarkable Polish mathematician, Henryk Zygalski. During World War II, the German military used a highly complex machine called the Enigma to create operational codes, and they firmly believed these codes were mathematically unbreakable. The Enigma was a physical machine filled with complex, rotating gears, but Zygalski and his team, they realized they could defeat physical gears with pure mathematical logic. Instead of just guessing the settings, Zygalski utilized advanced probability, complex permutations, and group theory to find patterns in the sheer chaos of the encrypted messages. In doing so, he pioneered the very cryptographic logic we use to protect our data today.
This brings us to his brilliant invention, the perforated sheets. Zygalski carefully calculated the mathematical permutations and cut specific holes into these large, specialized sheets of paper. When the sheets were perfectly aligned and stacked on top of each other over a light box, the light would only shine through the holes where the Enigma's complex permutations aligned. He literally found the light in the dark. His work proved that math is the ultimate tool for both making and breaking the strongest locks in the world. It laid the groundwork for how we decrypt and protect our digital secrets right now.
One single date. So many foundational stories. All right, let's make our final jump along the timeline. We're moving forward to July 15, 1965, to uncover the actual shape and structure of our modern digital world. I want you to try and picture the massive, overwhelming chaos of the modern internet. Millions of servers, billions of computers, trillions of messages flying around the globe every single second. With all that incredible noise, how does a tiny internet message, like a simple email to a friend, never get lost in that web? When data leaves your house, how does it know exactly which way to go to hit a specific screen halfway across the planet?
The answer to that structural mystery goes back to July 15, 1965, the day we lost a remarkable mathematical pioneer named Dudley Woodard. Woodard was a massive trailblazer, actually the second African-American ever to earn a PhD in mathematics. He mastered an incredibly complex field called topology, which was originally tied to concepts like two-dimensional analysis situs. To put it simply for us, topology is the math of shapes and spaces and what happens to them when they're bent, twisted, or stretched without ever breaking or tearing. Breaking down massive complex networks into manageable nodes and edges relies entirely on this abstract math. His groundbreaking work mapped out complex boundaries, the exact kind of geometric logic that lets computer scientists today structure a digital networks.
Woodard's work leaned heavily into core topological concepts, specifically things like the Jordan curve theorem. Basically, this foundational theorem states that any continuous, simple closed loop divides a plane into two distinct regions, an inside and an outside. Now, I know that sounds completely obvious when you draw it on a piece of paper, but applying this abstract rule to incredibly complex, multidimensional spaces is exactly what allows computer scientists to draw strict boundaries in digital networks. It's this invisible mathematical architecture that ensures your data routes perfectly and safely through the sprawling web of the internet without ever getting lost in the chaos. Bringing all four of these timelines together, we can clearly see how this one single date binds these brilliant minds: Abel Waffa, Mary Taylor, Henryk Zygalski, and Dudley Woodard. They were separated by centuries, yet connected by a shared, relentless curiosity on July 15th.
Every person we've met today, across completely different centuries and countries, fundamentally asked the exact same question. What is the mathematical pattern hiding inside the chaos? And because they were brave enough to ask, they found triangles in the stars, equations in the airwaves, logic in secret codes, and geometry